we mentioned that when we study a nonlinear system, we can write it only in this vector form, and we said that there are many equilibrium points. Now, generally, this will be the case. There are different types. There are things called isolated equilibrium points and non-isolated. When you've got an isolated equilibrium point, it's essentially some point where in a small radius around it, there are no other points. But when you've got a non-isolated point, it's something like a line of points. And in this case, no matter how small of a circle you draw around it, you will always be able to find other equilibrium points. So we're going to focus on the case of isolated equilibrium points. Now, how to study them? Remember we said that we're going to give up hope on trying to come up with explicit formulas for things. So what we're going to do is this technique called linearization. So when we've got linearization, remember that for a differentiable function, so if we take a function in calculus, it is generally nonlinear, but if we focus on a point, and if that function has a derivative, if we zoom in, it will be almost indistinguishable from its tangent line. And in that case, your function can be written as f of a plus f prime of a x minus a plus higher order stuff. And if we just choose to replace it here with its tangent line, so we could replace that, and this would be what's called a linearization. And all we need is some information about the derivative and the values nearby. And so again, this is some non-linear stuff, terms that are there. And we're effectively choosing to ignore these other terms. So for a system that looks like this, so let's say x prime is equal to f of x as a vector field, we'll be concrete and talk about a two-dimensional field. So we'll have some f of x and y, and we'll have y prime like this as some g of x and y. There is such a thing as a multivariable Taylor expansion. And let's say that we will have an equilibrium point that lives at x naught and y naught. It is possible to linearize or have a multivariable expansion about this equilibrium point, or sometimes it's called a fixed point. And what we could do is take that function, this f of x and y, and we could expand in a very similar way to what we did for the single variable function. The major difference here is that we've got multivariable functions, so we're going to have to take the proper expansion and the proper derivatives here. And we need to ensure that we've got a term for each of the first partial derivatives, and then we'll do the similar thing here for the next equation there. So this would be x prime, and this would be y prime. And we'll go ahead and we linearize. We do this multivariable Taylor expansion about these points. And so effectively what we're going to do is keep only the linear terms and throw away all the other stuff. Now, note that at the equilibrium point, each of these things, each of x prime and y prime is equal to 0. And that means that f of x naught and y naught has to be 0, and g of x naught and y naught has to be 0. So near the equilibrium point, we can effectively simplify things even further. We'll have f of x and y is approximately this first partial derivative at the equilibrium point times x minus x naught. Second partial derivative at the equilibrium point, y minus y naught, plus this higher order stuff. And similarly here, we'll just be able to write this. Now, if we make another substitution for the interest of making it easy to write and easy to read, we'll get the following. We'll let u equal x minus x naught, v equals v or y minus y naught. What we'll do is we'll have our vector now. We'll be able to take our vector and write it as x and y. We'll be able to rewrite this system here and effectively shift the center of this expansion from the equilibrium point to 0, 0. It just recenters everything for us where we need to. And if we were to do that, what you'll be able to see here is that if we were, the last thing I need to say here is you should hopefully be able to see that taking the derivative, x u prime is going to just give us x prime and y prime. So hopefully you will now be able to see that I'm able to rewrite this system and I can linearize the nonlinear system. And that means that I'll be able to have this u prime vector is this matrix of partial derivatives, df dx, dg dx, df dy, dg dy. Now, each of these is evaluated at the equilibrium point. And you can see that this is going to be multiplied by these individual components just like that. So we've effectively turned this into a linearization. We'll have this vector u prime. I'm going to call this matrix J, and it's J at x naught and y naught. It depends on the point we pick, times this vector u, plus some vector field of higher order stuff. And this is nonlinear stuff. And this is a technique we're going to use. And once we have this technique, we can then study what the equilibrium point does. We can study the equilibrium point behavior near this x naught and y naught just by taking these terms. So this is a technique that is useful. Now, there's some terminology. The system is going to be called almost linear if this nonlinear stuff is somehow small or negligible. And there's a simple test. The test will be given here. It basically will say you will be almost linear if the determinant, or I should say that this matrix J, if this J of x naught and y naught is invertible at that point. Now this matrix J is called the Jacobian matrix at that point. So we will be able to take a nonlinear system. We can always linearize it. And if we want to ensure that the stuff that we're neglecting is small and negligible, it will be lucky for us that all we really need to figure out is the determinant, is the matrix Jacobian there invertible or not? That can easily be done with a determinant. And if that's the case, then linearization is hopefully going to give us some useful results. So let's take a look at this. Let's try to see this in the context of an example. Here's an example of a nonlinear system, and we'll identify these components f and g. And the first thing we need to do with any nonlinear system is find the equilibrium point. So we need to determine where x prime is 0 and y prime is 0. So we need those simultaneously to be 0. So we'll need to solve x minus y is 0, 2x minus y minus x squared is 0. So the first equation tells us that y and x will always have to be the same. If we substitute this into the second equation, we'll find 2y minus y squared is 0. Or in this case, we'll find y minus y squared to be 0. y into 1 minus y is 0. So y is 0 or y is equal to 1. Now in each of these, because x and y have to be the same, that means we will get two isolated equilibrium points or critical points or fixed points. There are a lot of different names for them. They are indeed isolated. It's not a continuous string of points together that we can't separate. We can draw a little ball around these, and they will be the only point within that ball. So now, what we need to do is determine if these are almost linear. So we need to check the Jacobian at each one of these points. Now remember, the Jacobian at a point is given by this derivative, this matrix of partial derivatives at each one of these points. And we'll construct it. So what we'll need to do is to differentiate each of those functions that we've been given from our system. So df dx is simply going to be 1. df dy is simply going to be -1. Now dg dx, this is for the first time we're going to observe a non-constant. So that means that the Jacobian varies its values with location. So if we reassemble all of this, we'll find that the Jacobian at any point is going to be this matrix. Now what we need to do is evaluate the Jacobian at 0, 0 and evaluate it at 1, 1. So you can see here that this matrix will simply be as follows, and this matrix will be here. Now, to be almost linear, that means that these Jacobian matrices need to be invertible at these given points. Now, being invertible, it's very easy to check. What we need to do is check the determinant. So you can see that the determinant of this Jacobian at 0, 0 is simply going to be -1 minus -2, which is 1. That means it's invertible, and that means it's almost linear. And the determinant of the Jacobian here at the point 1, 1 is going to be -1. So again, these are both almost linear. And that means we are hoping that this linearization idea will tell us something useful. Now, what do we do with this? What we're going to do is check the behavior. And the behavior, that means we are going to need to find the eigenvalues of this Jacobian matrix. That's the point of the linearization. We take a system, we write it in linearized form so that we can apply all of the results and the techniques we had from before. We would like to determine what the eigenvalues are going to tell us about these systems at these points. And we're hoping that because the nonlinear contribution is small, we hope that we'll get something meaningful. So if we were to go ahead and plug everything in here in terms of finding the determinant, finding the eigenvalues, what this will lead us to is a lambda squared plus 1 is 0, so lambda will be plus or minus I. Now immediately we know that when our eigenvalues are purely imaginary right here, that means this analysis tells us we have a center. Now, if we were to do the same thing with the Jacobian at 1, 1, the Jacobian matrix is a little bit different in this particular case, but if we were to go ahead and build it and construct it here, what we would find is something similar. We would find that we'd get lambda squared minus 1 is 0, so lambda would be plus or minus 1. And that means we would have a saddle. So this idea is to say, take a nonlinear system, in some way zoom in really close to the point you're interested in, the equilibrium point, and then see if the linearized version of the system tells you something useful. Now, this type of approach told us that at the origin of our system, 0, 0, we would have a center. And if you look at the origin here, you can see that, hey, there are some closed trajectories around. And at the point 1, 1, so that's roughly here, we're expecting to see a saddle. And that means, again, we've got some trajectories that seem to go like this. So all of these things seem consistent with what this linearization is telling us. So this seems to be consistent with the nonlinear phase portrait. But you may or may not notice that something interesting is going on here. And it has to do really with the center. If we take a look here and we kind of back off the center a little bit, what we're seeing is that we've got some closed orbits. But the further we back away from that center, we can see that the orbits here no longer seem to be closed. There comes a point where they switch from being closed orbits to something else. And so that's a bit of an issue. The center at 0, 0 doesn't act like a center if we back off, if we move away from 0, 0. So that's somewhat interesting. And this is a feature of nonlinear systems. And it's an important point that we can say something general about. Here's a useful theorem about almost linear systems. So if you have an almost linear system, so remember at the equilibrium point, if the Jacobian is invertible, if you go ahead and you classify the equilibrium point of that almost linear system, what this theorem is saying is it's going to be the same type and stability as the equilibrium point of your linearized system. That means the nonlinear system behaves like the linearized version. But there are two special cases. So one of the cases is when you've got a repeated eigenvalue. And in that case, we're not really sure of the type, right? It might be a node, it might be a spiral, but we are sure of the stability. So we'll know if it's stable, if it's attracted to the point or repelled from the point. If the linearized system has imaginary eigenvalues, purely imaginary ones. Now, this is the case where, once again, we are unsure of the type. It might be a center, it might be a spiral. And furthermore, we don't know what the stability is going to be. We are not sure what the stability is going to be just from that linear analysis. And so some classifications are in order here. When we've got points, when we talk about stable or unstable, there's something called asymptotic stability or asymptotically stable. So this is when you've got some equilibrium point and any x of t and y of t, they have to approach the equilibrium point as time goes to infinity. So it doesn't matter how far away you are. If you, well, I shouldn't say that. If you're kind of close, if you start somewhere close to your equilibrium point, at some point you will just have to get sucked into it. There's no way around it. That's what asymptotically stable means. So this is the kind of thing we think of when we think of sinks or stable spirals. Everything kind of gets sucked in. If we are unstable, we don't get pulled in at all. So we don't have to get close. We don't get close at all. And this is the kind of thing when we think of a source or an unstable spiral. Now, there's something that's just called plain old stable. And when you have a stable equilibrium point, if you start close or near to the equilibrium point, you stay close. But you don't necessarily get sucked into the equilibrium point. It's not necessarily true that you converge. So this is what we talk about when we think of centers, for example. We don't necessarily have to get pulled in. So we could stay somewhere in there and we might just float around. We might move around in there, or there might be some other complicated behavior. So the theorem above is telling us that, hey, look, if we've got a saddle point, or if we've got a sink or a source, it's going to stay like that in the actual nonlinear system. The only fishy case is when we've got a center. It might be a center, it might be a spiral, it really can't be determined. Furthermore, like I said in this example above, when you've got a center, it may not stay as a center. That's a big difference from linear systems. Now, a note, when you've got a linear system, the stability and the type never change for your equilibrium point of 0. It never changes. It's always the same. That isn't true for a nonlinear system. Now, finally, a good question you might have is, well, what can we expect from our nonlinear system, so in this vector form, if it is not almost linear? And in that case, lots of strange things can happen, strange behaviors that are not seen in linear systems or linearizations or linearized versions. So we're used to things like centers, or we're used to things like spirals. In a nonlinear system, you can get far more complicated behaviors. Here are two phase plane portraits, direction fields, of non-almost linear systems. These kinds of behaviors at these equilibrium points, in both cases, the equilibrium point is at the origin, and there's a whole bunch of strange stuff going on here, right? These aren't centers. These aren't saddles. These are nothing like things we've seen before. And that's what makes nonlinear systems both complicated and very interesting. The kinds of behaviors you can get are out there.